We spend so much time designing systems for stability. But what if that very effort is precisely what causes them to break? In any complex project, building a company, writing software, managing a supply chain, the goal is always the same. You want to create a system that's stable, predictable, and resistant to failure. And yet they do. In fact, the very systems that we've optimized for perfect stability are often the ones that fail the most catastrophically. There's a contradiction here, isn't there? Some kind of hidden force at play.
And when the failure comes, it's not some gradual decline, it's a sudden collapse. One moment, the system looks perfectly fine, better than ever even, and the next, poof, it's just gone. This isn't an accident, it's a feature.
To really understand this mechanism, we're going to watch a simple physical system. Let's just picture a wild, untamed river. It's going to be our model for this whole process. So, Section 1, the logic of control. When we're faced with a complex, unpredictable system, our first impulse is to try and control it. And this logic is completely rational, it's methodical, it's all about preventing known problems. The whole process kicks off by identifying potential threats. You make a list of everything that could possibly go wrong based on all your past experiences. Fire, flood, a power outage. It seems like the most logical first step you could take.
And of course, this gets formalized. It's called a business impact analysis, and organizations spend enormous resources doing this, identifying their most critical functions and trying to figure out exactly how these known threats could knock them out.
Pretty soon, control just becomes a set of metrics. How fast do we need to recover? That's your RTO. How much data can we afford to lose? That's your RPO. Every little aspect of a potential failure gets quantified because we believe if we can measure it, we can manage it.
And all this rational thinking leads to one inevitable action. For our wild river, the logical response to the threat of a flood is to build levees. You contain it. You control its variability.
Section 2, the price of silence. But this control, this stability we've worked so hard to impose, it comes at a cost. There's a hidden price that the system pays for being so quiet. You see, those small, frequent problems we worked so hard to get rid of, the minor floods, the little system glitches, they weren't just annoyances. They were information, crucial information. They were teaching the system about its environment, testing its responses when the stakes were actually low.
By getting rid of that feedback, we've effectively made the system blind. It no longer gets those little stressors that would force it to adapt and adjust. It's losing its connection to reality.
And yet, on the surface, everything looks perfect. The metrics are all green. We interpret the absence of minor problems as a huge success. The system is performing exactly as we designed it to. It looks more stable, more robust than ever before. This illusion of safety actually encourages us to take on more risk. Because we trust the levees, the city expands and builds right up to the walls. All the other options, like building farther away from the river, are abandoned. Why? Because they're less efficient. The system is now locked in. Which brings us to Section 3, the fragility paradox. This is the central puzzle. The very drive to eliminate all risk has created a new, hidden, and frankly, much larger vulnerability. Okay, think about it like this. There are two basic ways a system can respond to stress. One type tries to resist the shock, and if it survives, it just stays the same. The other type, though, it actually gains from the shock. It gets stronger. That first behavior is what we almost always aim for in conventional design. We call it robustness, the ability to resist all the shocks we know about and just stay the same. But that second type, the one that gains from disorder, that's called anti-fragility. And this is the critical part. It is the precise property that we have systematically engineered out of our system. By preventing all those small shocks, we've stopped the system from ever learning, adapting, or getting any stronger. Now let's go back to our river. Because the levees prevented those small floods, silt has been building up on the riverbed for years, raising it higher and higher. The water itself now flows high above the city, held back by walls that have never actually been tested by a major event. A huge amount of potential energy has been quietly accumulating, completely unseen. And at this point, there is no going back. The system is locked in. For the sake of efficiency, we got rid of all the other ways of doing things. The entire city now depends completely on those levees holding.
The cost to move the city or to change the whole system is now just too high to even think about.
So now the stage is set for the final act. An act that was made inevitable by the very same logic we thought would prevent it.
Then, a stressor arrives. But it's one that wasn't on our original list of threats. It's a storm bigger than anyone predicted. A strange combination of events that nobody could have possibly foreseen. It's the unknown.
And the levees fail. Not by a little bit. Completely. The system, so perfectly optimized to handle a specific set of known conditions, has absolutely no capacity to handle the unknown. The failure is total.
After, everyone sees the collapse as a tragic failure, a broken system. But it wasn't broken. The collapse was the ultimate expression of its design. The system was simply and perfectly obeying the rules that we had given it.